And spatial means whatsoever has been used, things stored near to that in the memory location will be used again. So these are the two things that while we discussing the locality of reference we consider. So temporal effect aspect of locality of reference suggests that whenever information is first needed, this item should be bought into cache where it should be kept as long as you are going to reuse it. And similarly, whenever you are bringing something in the cache, you should bring something that is closer to what it is. This what is closer to what we are bringing. So in a way, we does not bring a single instruction or single line. We bring the block of memory, or you can say block of data, or you can say block of instruction. Another term that is used for this is cache block or cache line. So whenever we bring something from main memory to cache memory, we does not bring a single item. Rather, we bring a set of contiguous address locations of same size, and that we call as cache block or cache line. Right? Now there are few important things that has to be understood before implementing the cache. Of course, first is the structure of cache. And another is the replacement algorithm. And then okay, first let's discuss these two things and then I'll discuss. So structure of the cache means in what way we are going to store these blocks into cache. That we refer as structure of the cache. And replacement algorithms means, I'll discuss of course in detail all of these things with all the variants possible. So replacement algorithm means while you are doing this process where you are bringing something into cache, you are using in memory. So there will be few times when you will not be able to get the data or instruction in the cache. That we call as miss. And when we get it, we call it hit. As long as hits are going, it's fine. When miss is going, you will figure out that this is not available with the cache. You will go to main memory. In memory, you will figure out the block where that particular information is. You will bring the block into memory. If cache, of course, in the cache memory. If cache memory is not full, it is empty, it's fine, you will bring it on. But in case if it's full, you have to remove something from the cache memory to keep this data in the cache memory. So while doing this, you have to do certain kind of replacement by which you are removing something that was earlier there and putting something new that was not there. So how to do that? That comes under replacement algorithm. Right. Now there is one or two more things that we have to understand. So whenever there is a request from processor, so there are two possibilities. Either there is a read request or this is a write request. And for both of the cases, there are two possibilities. There may be a read hit, or there may be a read miss, or there may be a write hit, or there may be a write miss. Fine. So when there is a read hit taking place, not a problem. The data will be sent to the cache from the sent to the processor from the cache. What if there is a write hit happening? So what may be the problem in case of write hit? Can somebody tell me? Hmm? Hello.
Yes, a little bit thinking.
So what will be happening in the case of write hit? Answer anybody? Okay, so in case of write hit, actually what you are doing, there is a processor, there is a cache, there is a main memory. In cache, you have brought something from main memory, and in process of writing it, you are changing this to something else. Whereas in main memory, it is of different kind. So there is an inconsistency between the cache memory and the main memory. So how to deal with this inconsistency? That is another thing that we have to understand. So there are two ways to handle this problem. One is you can use write through mechanism, and another you use write back or copy back. Anybody aware of these two things? Hmm?
Sir, about back, sir, I know a little bit about write back.
Yeah, tell me.
Sir, we can when we update, we write to the cache block. We can store a flag bit with it.
Right, right,
And whenever we are removing that block from that particular memory bit from the cache, at that time we can update the memory.
right. So there are two ways by which we can do that. One, of course, as your friend told, write back. So in which whatsoever you are writing in the cache, you flag that as dirty bit or modified bit, and eventually, after some time, you update it in main memory. So the blocks that are having dirty bits, those are updated in main memory. Another way is while updating the main memory, you can directly writing you can directly write to main memory and cache memory both. Now, can you suggest tell me which one is better and why?
Sir, I think the second is better.
Okay, why?
Sir, because while the memory is in cache, it's being written or updated many times. So if we write at the same time in both cache and memory, then there would be many operations.
Yeah, so I mean there are both the possibilities. So if something is being written again and again, in that case there will be a problem that you are writing all the time to the memory, while just in write back or copy back approach, uh, it can be ensured that these multiple writings are not actually affecting the things. But again, I mean, if it is not happening, maybe you are writing whole block and that is causing another inefficiency, or you have to take care that while because your main memory also taking data from secondary memory. So there is a possibility that you are taking. So, for example, you are loading something else from secondary memory to main memory, and for that you are removing something from main memory. Of course, by sending it back to, by updating it back to the secondary memory. In that case, you have to ensure that whatsoever changes have been made, that should be reflected properly, right? So, I mean, write back or copy back, of course, gives you better efficiency, but uh, that may lead to certain complexities. And if there are no multi writes happening, the efficiency may also not be very good. Does it make sense to you guys?
Yes, sir.
Any questions about this?
No, sir.
Okay. Now let's talk about the uh, read miss and write miss. So whenever a read miss happens, the idea is simple. That means that there is some data that is not in the cache. So uh, a block of words, as we have already said, that a block of words will be actually brought from the main memory to cache memory, and that will be used. So there are two approaches. One is the complete block from main memory can be brought to cache memory, and after that it may be transferred. And another thing is you will bring the complete block, that's right, but suppose for example you need this word to be used. As soon as this word will reach here, you will transfer it to processor, and then processor can use it. So of course the second method, that is called as load through, or early restart, that is of course more efficient in terms of time, because it is not waiting a complete transfer to happen, but this needs a little complex circuitry. So this is another trade-off that one has to make, whether you want to use this or not. And then if there is a write, is it okay? Does it make sense? load
Yes, sir.
through and early restart. And then if there is a write miss, that means where there a write has to happen, that thing is not available. Then there are two possibilities. Either a write through protocol can be used, so information will be directly written into the main memory, and in case of write back, the block will be brought to the cache, and the desired writing will happen. So, I mean, depending on what protocol is being used, either it will be a write through one. You don't have to write into the cache. You can directly write into the main memory. And in case of write back, you can bring it to cache, and write that, and eventually you will update it in the normal process of write. So these are the general things that we are going to discuss about. So let's first of all let's discuss about the structure. So for structure we use a word mapping function. So how main memory and cache memory maps, that is called as mapping function. We are taking here an example where we are talking about a cache with 128 blocks of 16 word each, and then so what will be the cache memory size here? Can somebody tell me? Hmm? What will be the cache memory size here? कितने वर्ड्स होंगे इस कैश मेमोरी में? हेलो, हेलो,
You're audible, sir.
या सो इस कैश मेमोरी का साइज क्या होगा?
16 words in 128 blocks would be. So word size we are assuming to be 8.
Tell me in terms of words only. That is also fine. I am not
One
talking in terms
128
one.
into 16 words then.
So what will be that?
That would be 2048.
Yes, so this will be 2048. That you say is what? 2K words. And assume that main memory has 16 address lines. Or 16 bit of address. So how many words will be there? Hmm?
8K.
8K? Just think properly. We've seen this number earlier as well with 16 address lines. So that will be 2 raised to the power 16 words. What will be this number? That will be 64K. And how many blocks? For example, here we are talking about 128 blocks of 16 words each. How many blocks will be here of 16 words? How many blocks will be there?
The 4K.
4K blocks. Right. So just to awake you. So now we discuss three kind of mappings. One is direct mapping. Sorry. Another is associative mapping. And another is set associative mapping. So starting from direct mapping, this says typically that every word in main memory has a defined location in cache memory to store. इसका क्या मतलब है? इसका मतलब ये है कि मेन मेमोरी में जितने भी वर्ड्स हैं उन सब के लिए कैश मेमोरी में कोई ना कोई फिक्स स्पेस है. But is it possible? How will it be possible? You understood what I am saying?
Yes, sir. But in this case, won't there be repetitions for if every
Yes,
location is
there
fixed
will
because
be
memory is very large?
there will be conflicts. There will be repetitions and there will be conflicts. So that means every location in the cache has got a fixed number of blocks that may be stored there. Of course, that location is one only. So out of this, and this, any of those will be stored. And if one of more than one will come, so then we have to decide which one to store. So maybe the one who will be coming later will be replacing the first one, right? So for example, in this particular case, what we will do, we will take the, let's say the block number is J in main memory. So we'll just compute J Moldo 128. So for example, if it is block number 0, it will be stored in 0th location. If it is 1, it will be stored in first location. If it is 2, it will be stored in second location. If it is 128, where will it be stored? Huh?
Zero location.
0th location. If it is 129, it will be stored at first location. So that means at 0 location, what all you will be storing? So you'll be storing 0, 128, 256, and likewise. And at one location, how many possible locations will be? How many possible blocks will be there? Just can you tell me? You know the size of cache memory. You know the size of main memory. So for a particular location, how many candidates will be there?
So 4K divided by 128.
4K divided by 64K divided by 128.
One
No,
28 blocks.
4K divided by 128. So what will be the value?
128 blocks.
128 blocks or 32 blocks? Just do it properly. I think you missed something in doing that, or I missed something. Tell me.
Sir, please show the memory size again, sir. Which was written. Please show the memory sign again, size which was written above.
That is 64K words or 4K blocks. Whatever way you want to call it, both are fine for me. Okay. So 4K means 2 raised to the power what? 12. And 16K means, sorry, 2 raised to the power 12, and 128 means 2 raised to the power 7. So 12 minus 7 is equal to 5. So 2 raised to the power 5 is equal to 32. Fine? Is it okay?
Yes, sir.
Fine. So you are having a 16-bit of address. That 16-bit of address will be divided into 3 parts. One will be used for word, another will be used for block, and another will be used for tag. Let me tell you what it is. So we have a block of how many words?
16.
How many words block? 16. So to figure out which word it is in the block, how many bits are required? अगर 16 वर्ड्स का ब्लॉक
So
है
5.
तो हमको ये 4, right? And cache memory is of how many words? Sorry, how many blocks?
82.
82? 128. What is 82?
So
What is
7
it?
bits.
82 नहीं से 32.
8 blocks. Pardon?
So
7
32
bits.
blocks. ना अभी तो ऊपर निकाला था 32 blocks cache में.
मैंने ये कहा कि 32 डिफरेंट ब्लॉक्स उस पर्टिकुलर लोकेशन के लिए कंटेंडर है, बट कैश मेमोरी तो 128 ब्लॉक्स का है ना.
हाँ ओके हाँ तभी गलत हो रहा था.
ठीक है. तो यहाँ पर कितने बिट्स लगेंगे?
7.
7 और 32 कंटेंडर्स हैं, तो टैग हमको हर लोकेशन पर एक लगाना पड़ेगा, और वो कितने बिट का लगाना पड़ेगा?
5.
5, जिससे हमको ये पता लग पाए कि मेन मेमोरी का कौन सा वाला ब्लॉक यहाँ पर आया है, क्योंकि वो तो 32 में से कोई भी एक आ सकता है. तो which one has come out of those 32? So for that we will be doing this. This is a very simple mapping. If you understood it, it's fine. Tell me if there is a doubt. Please ask. You understood it? So it will typically look like block 0, block 1, block 127. And for main memory, so I'll just denote it like this, I'll just denote it like this, I'll just denote it like this. For main memory, how will it be like? So block 0, block 1, or I can probably change the color.
Sir, how are we dealing with conflicts?
What are you saying?
Sir, how are we dealing with the conflicts?
So for conflict, it is simple. Suppose there is a block 0 at block 0 and block 128 comes. So block 0 will be replaced. Right?
So the newer block replaces the old block.
Older block. Fine.
Okay.
So what is the problem with this? This algorithm is pretty simple. What is the problem with this algorithm? Can somebody tell me?
Sir, in case the 0 block is again required in that case.
So 0 block is again required, that will be brought again. And because of locality of reference, it is not very likely that, two very distant blocks are required again and again. So what is the problem with this? Can you suggest me? So the biggest problem with this kind of thing is efficiency. You said that you replace data when you have your cache memory full. There is no space available, then if you bring something, you actually replace that. But here, you are doing even when you don't have your cache memory full. So that is possible that this block is entirely empty, and even then these blocks have to be replaced. Are you getting my point? So you are not using cache memory efficiently. That is the problem. So it is easy to implement but inefficient and inflexible. Make sense? Is it okay?
Yes, sir.
Okay. Another thing is associative memory. sorry, associative mapping. Here idea is pretty simple. Bring as long as you have space. So you are not fixing any position for any memory. You just bring it, and that's okay. So like in the previous case, you partitioned it into 128 different blocks, and all the blocks are fixed for few blocks in the memory. Here nothing of this kind will happen. Here of course blocks are 128 but nothing is reserved. So for example here block 4 may come, then here block 8 may come from main memory. These numbers are main memory. Block 0, block 300, block 50, and likewise. Right? Does it make sense? Is it okay? Does it make sense to you?
So please repeat it once again.
So it's simple. You have total 128 locations. You can bring whenever you need something, you bring from main memory, put it here, and whatsoever next location is available, you can put it there, as long as it is not full. Once it is full, you will bring some. You want to bring something, you replace it by something. So some replacement algorithm will be needed. That's fine. But memory organization, memory structure is very simple. You will keep on filling it. Once you are filled, replace something and bring new. Then again replace something and bring new. Right?
Yes.
Make sense?
Yes.
So here all the blocks will be having a tag. Can you tell me what will be the size of tag here?
Well,
Yeah, of course, 12-bit tag. Because you have total 16 bits of addressing, and one block contains 16 words. That means 4-bit of addressing will be taken care of by this. So you will be having tag of 12 bits. Right. The associative mapping always needs a good replacement algorithm. We'll talk about replacement algorithm after some time. Further, whenever you are going to take something from cache memory, you have to scan your all the 128 tags of 12 bits. 128 tags of 12 bits. Because even it is not sure that they are in order. So you have to scan all 128 tags of 12 bits to determine whether a given block is in cache or not. So this brings some additional cost of memory access in terms of delay. So this is, a problem with associative memory. Right? You understood what I am saying?
yes, sir.
Okay. Now there is something that is in between of both the your direct and associative mapping, that is called as set associative mapping. So here blocks of cache are grouped into sets, and mapping allows a block of main memory to reside in any block of the specified set. So, I mean, now you are partitioning your cache memory into some parts, and whenever you are bringing something, you are bringing it to a particular set. So it is not that it is one to one. So like there for one block, there were 32 candidates. Now it is not like this. So for example, you have a set of, let's say, 4 blocks each. So for 4 blocks location, how many candidates will be there? So 128 candidates will be there for these 4 blocks. But it's not that if one is coming, other has to be replaced. It has to be replaced only if these all 4 are full. Right? Is it okay?
Yes, sir.
So suppose if you have a 16 block set. So that means you'll be having a 4-bit set field in that case. And after all those 16 have been replaced, then only it will be actually all 16 places have been filled, then only it has to be replaced. So one extreme condition may be the block size is 1, and another extreme condition is block size is 128. If it is 1, then what it will be called? Huh?
Sir, direct mapping.
It is direct mapping. And if it is 128, what will it be called?
Associative mapping.
Associative mapping. So this way it will actually change. Right. Now, after discussing these all 3 mapping techniques, any confusion about these mapping techniques? First, let me know this, then I'll go ahead.
No, sir, please go ahead.
So there is one control bit that is called valid bit. So what this valid bit does? So valid bit tells you that whatsoever is stored at cache, that is actually of use or not. So what does it mean? So when you power on the system, so what you do, you use DMA to transfer your OS or related things to your processor, or from secondary memory to main memory. So from secondary memory to main memory to processor. So DMA actually performs this, and cache is generally bypassed for this because it's an initial thing and it is all fixed that what has to come. So cost and performance reason, it is bypassed, and all the blocks of cache is assigned 0 as this valid bit. When first time this block, any of the block is used, so let's say block number 12 is used for the first time, this valid bit for block 12 will be shifted from 0 to 1. So if this valid bit is 1, that means that now it is actually of some use. Before that, whatsoever written here is a stall, useless thing. So, that was some garbage that need not to be looked upon. Fine.
Yes, sir.
So now just see a tag of sat associative where I am having 64 sets of 2 blocks each. So first thing is of course in a block word, that is 4. And then because there are 64 sets, so there will be 6 sets, and then out of this tag will be 6, because you have to figure out which one is this one, right? So this will be the kind of address distribution for this. Does it make sense?
Yes, sir.
Now there is one more thing that has to be discussed in this, that in fact I have discussed earlier. So when there is a DMA transfer from main memory to secondary memory, and write back protocol is used. So what will be the problem? Because write back protocol is used, so there is a possibility that whatsoever you are transferring from main memory to secondary memory, that is actually not updated, right?
Yes, sir.
This problem is called as cache coherency problem. Right? So to solve this cache coherency, the solution is to flush the cache before making this kind of transfer. So while flushing the cache, you are forced forced to update it at the time only. Now you cannot wait for anything for write back, right?
Yes, sir.
So these details are about the structure of the cache memory. Now, one thing that we talked about is replacement algorithm. So now let's talk about replacement algorithm. So normal intuition says that a replacement algorithm should be should work in a way that whatsoever is being used last, that should be replaced, and whatsoever is currently in use, that should remain in the cache memory. So I am going to discuss an algorithm that we call as LRU. This is one of the most famous algorithms, that is called least recently used replacement algorithm. So idea wise it is pretty simple. You will replace something that you have not used since long. So you will preserve those things that are actually being used recently. Something that has not been used since long, that will be replaced. But now the question is how to figure out this, that what has to be, I mean, what is not recently used, or what has been recently used. So keeping this track is itself a problem. So for that we use a counter. So for example, we are talking about a 4-block set associative cache. So with all these 4 blocks, a counter of 2-bit counter will be added. How this 2-bit counter will work? So when there will be a hit, so for example, for this block, there is a hit, its counter will be reset to 0. Fine. And other counters, so for example, here the counter value is 1, here is 2, here is 3, things like that. So this will become 0, this will be incremented by 1, this will be incremented by 1. Right. And when there will be a miss occur, and suppose there is no place available here, so suppose it is all filled, and a miss occur, so the one who will be having highest counter value will be replaced, and the new block will be placed at its location, and this will be given a 0 value, and other counters will be incremented by 1. So this way this algorithm works, and I mean, this is a useful way of doing this. There are other algorithms also that works on older blocks to remove, but this is actually more implementable algorithm. There is one more algorithm that simply says that don't look at anything, replace any random block. And interestingly, that also performs fine. So performance wise, that is also fine. There is not a much problem with the performance of that algorithm. Now, let's move on to,
Sir,
yes,
so what is the initial value for the counter?
0.
0 for each.
Yes. Fine.
Yes.
So now let's move on to performance consideration. So students are decreasing all the time. Now it is 19. is something called price performance price performance ratio. So while we are talking about performance ratio, we are interested in price and speed. So you cannot only talk about price, or you cannot only talk about performance. You have to see that your price should be minimum and your performance should be maximum. Otherwise, if you don't have a problem of price, you can do anything, whatever you want. So, we always go for the methods where we can get the performance best with the low price. So, one thing that can be done with main memory is like this. So, main memory generally comes into form of blocks. So there may be, let's say, if it's a 8 GB memory, maybe there will be 8 blocks or 16 blocks or likewise, or maybe 4 blocks. So one thing is data can be stored in one block fully, then data can be stored in another block fully, and then data can be stored in another block fully, and then data can be stored in another block fully. Another way is data can be stored in parallel in all 4. So if some kind of parallelism can be introduced, that is actually going to increase the speed. So for that we use something that is called interleaving. So what does it mean? So I will just quickly tell you what does it mean. So let's say that I have a memory with n modules. And these modules, all of them have their address buffer register and data buffer register. All memory modules have this. And this is module 0, this is 1, and let's say this is n minus 1. So one possibility is, let's say if you have to store a block of k words, you will simply keep on storing here. And another possibility is you can, store one word of the block here, another word of the block here, another word of the block here, and another word of the block here, likewise. So the second technique is termed as memory interleaving. Now let's see how it actually benefits. So we'll see it by an example. So suppose that we have a cache of 8 word block, and there is a miss. So the block that contains the desired word must be copied from main memory to cache. And let's say that memory is built with relatively slow DRAM chips. So first word need 8 cycles to access. You remember while I was discussing DRAM, in a block transfer, first word, because you have to find address and all, needs more time, and let's say after that 4 cycles are needed to access, right? So if there is a single memory module, so what all will be needed is actually you have to transfer, I mean, so let's say one clock cycle will be actually for uh, telling that you need a transfer to be done. Then 8 will be for accessing first word, and then there will be 4 cycles will be requiring for 7 words, so 7 into 4, and then 1 will be required, let's say, for transfer to complete. So that makes it 38. Now let's assume that you have 4 blocks, 4 modules in memory with interleaving. So in that case, what will be the requirement? So 1 as earlier, 8 as earlier, and this 8 will be for 4 different blocks. So 8 plus, now in every module there are 2 words. So first word will be requiring, I mean, you have to figure out an access. So you have to do 8, and then 4 for the second word, and then 4 for the transfer. So that means 17 cycles. So you can see that there is a substantial difference if you are shifting from module to right. Is it okay? Does it make sense?
Yes, sir.
How many pillars today? Okay, 19 are still there. Fine. Now let's talk about something for hit rate and miss penalty. So hit rate is called when you go for looking out something at cache and you find that out. So at that time you say that you have got a hit, and when you miss it, and then because of missing you have to go to main memory, and then you have to transfer it to cache, and then you have to transfer it to processor. That time that you spend is termed as miss penalty. It depends on the organization of cache and everything, that how much, and replacement algorithm, that how much you will be getting the hit rate. Generally, there are 2 things that you transfer, that is data and instruction. Any idea which will be having better hit rate? Any idea which will be having better hit rates? Hmm? So instruction will be having better hit rates because there is a limitation of the instruction, and suppose there is a loop that is already there, or there is a function that is being called. So some instructions will be repeatedly used, many times used. So generally instructions will be having better hit rate, and generally we got hit rate as much as 0.9. So assume that you are having a hit rate of 0.9 for data and 0.95 for instruction. Now in this case, let's see an example that to understand that with cache and without cache, how will it be like. So I mean, let's assume that H is the hit rate. So average access time will be H multiplied by the time to access the information in the cache. Let's call it C, plus 1 minus H times the time required to access the main memory. Let's call it M. So this will be my average time that will be required depending on the hit rate. Now let's see an example. Consider a case when there is no cache and you need 10 clock cycles for read, write or read. And then another case when there is a cache with 8-word blocks and interleaved memory. And assume that in both the cases 30% of the instructions need a read and a write. So if 30% of the instructions need a read and a write, so 30 plus 30, 60, so 70 plus 60, that will be out of 100 instructions, there will be 130 memory accesses. Right. And with no cache, we have already said that it is, 10 per cycle. So with no cache, it is 130 multiplied by 10. And with cache, because you will only write in data, will not write in instructions. So, and we assume that when there is a read, that are instructions. So 100 multiplied by 0.95. We said for instruction it is 0.95. And for cache, assuming that one cycle will be needed, plus 0.05 multiplied by 17. We have already computed this 17 earlier. Plus 30 times 0.9 multiplied by 1 plus 0.1 multiplied by 17. If we divide these no cash and with cash thing, that comes out to be 5.04. So with 90% and 95% hit rate, you got as much as 5 times better performance in presence of cache and interleaved memory. Does it make sense? Hello?
Yes, sir.
Hello? Are you able to understand this?
Yes, sir.
Should I go ahead or should I stop here? You are able to understand?
Yes, sir. Yes, sir.
Or just should I discuss something more?
Yes, sir.
Okay. So now let's assume we are considering a case where our complete memory is cache, and when our we have a cache with 90 and 95% hit rate. So in that case, now denominator will be coming in numerator, and numerator denominator will now become just 130 because it is complete cache, so only one cycle will be needed for anything. So it will be, let's say, 100 95 into 1 plus 0.05 into 17 plus 30.9 plus 0.1 into 17 divided by 130. If we compute this, this comes out to be 1.98. So if you are having full cache, that is way expensive, and if you have a cache with 90 or 95% hit rate, it is only 2 times of difference. It's not beyond that. It's just 2 times of difference. So that means having a cache with a reasonable hit rate is actually something that gives you a lot of performance improvement. And if you have a complete cache, that will improve the performance certainly, but not up to a great extent. So now the question is how to improve the hit rate. So one is, of course, you can increase the size of cache, but that is not a very good idea because ultimately it is coming with a lot of cost, and we have seen that increasing is actually not as rewarding as the cost of it is going to be. Then another possibility is to take the advantage of spatial locality. So if let's say items in a larger block are needed for computation, then it is better to load these items in the cache and avoid the chances of miss. So in a way you can increase your block size, and you can decrease the possibilities of hit. But then increasing the possibilities of block size beyond a certain label will actually decrease the number of blocks available, and eventually you have to replace blocks more swiftly. So you can improve the hit rate and decrease the miss rate by taking the optimal size of the block. If you'll go it, if you'll go much higher, your miss rate will increase. If you'll go much lower, your hit rate will decrease. So some optimal values should come. So generally, 16 to 128 byte size for block is considered as most optimal. And of course, that one thing that we have already discussed, that is early restart or load through. So I mean, when your block is being transferred, just you start using word immediately without waiting for whole block to load. That is another way by which you decrease the miss penalty, though it is not increasing the hit rate, but miss penalty is getting decreased. So that is actually another thing that is useful. Now, where to put this cache? So one possibility is you put it on processor. Putting on processor will give you certain advantage, and that advantage is, I mean, you don't have to make a transfer from chip to chip, and from chip to chip transfer takes time. So putting it on the processor is the best possible location where you can put it. But then putting it on the processor will eventually lead to space consumption in the processor, and that is actually expensive thing to happen. So you need processor space for other things, but definitely you can use certain space for that. So that's why we have two kind of caches. One is called L1 and another is called L2. L1 cache is kept into processor, and L2 cache is kept into outside the processor. So, I mean, what is done in that case? So, first of all, processor looks at L1 cache, and then processor looks at L2 cache. And if it is not available at both the locations, it goes for main memory. In that case, the time T average can be written as H1 C1, where H1 is the hit rate of memory cache memory 1 L1 cache. C1 is the access time for L1 cache, plus 1 minus H1 when it is missed from L1 cache, H2 C2, plus, I mean, H2 is the hit rate for second one, and C2 is the access time for second one. 1 minus H1, 1 minus H2, M. So this becomes the average time required for this. And if H1 is equal to 0.9 and H2 is equal to 0.9, up to 99% cases, you actually get, you can see that you actually get the data in the cache itself. So, I mean, this is about the location of the cache, how it matters. L1 cache may be faster, but then you cannot have a bigger L1. But then L2 cache may be slower, but you can have a bigger L2 cache. Any questions about it?
No, sir.
Okay. So I'll just quickly discuss one more, in fact, two more things, and I'll just finish it off for the cache memory, and next we'll be discussing in the next class. So, apart from all these things, there are few more things by which you can actually improve the performance. So first of them is write buffer. So when write-through protocol is used, so write-through means you're directly writing to the main memory. So processor has to go and it has to write to the memory. Memory is not really very fast thing. So processor has to wait for memory to write everything and say that now it has written. So that actually slow down the performance. So to improve the performance, we introduce something that is called write buffer. So a write buffer is something that is a temporary storage for whatsoever processor wants to write into the memory. Processor simply places a write request into the buffer, and then it goes for its next instruction. And these write requests remain stored as long as main memory is not able to write that completely. So this helps in actually performing the read request immediately, and read request should be actually performed immediately because the processor may be waiting for that. So because of this write buffer, memory is not bound to do this write thing first and then perform read after that. It can perform the read first, and then after that it can actually take the write request from the write buffer and perform that. So this write buffer may hold a number of write requests, and it is possible that a read request is coming something that was recently changed by processor, but that has not been written to the memory. So that is still with write buffer. So in that case, this addresses of the data to be read from memory are compared with the addresses of the data in the write buffer, and if there is a match, the data will be taken from write buffer. So this way, write buffer actually improves the performance if there is a write-through protocol. If there is a write-back protocol, the write operations will be performed in cache. But when new block of data has to be brought into the cache, this has to be removed. So then this has to be removed. So in that case, cache has to go to memory and it has to wait for its writing it down, and then only it can come back and take the new data. And that will keep the processor on hold for some time. So to avoid this, again this write buffer can be used. This cache will go to this write buffer. So there will be a write buffer. Cache will directly go dump the data there, and it will keep on transacting with memory, and then cache will be taking data from this. So here also, this works well for the write back protocol, and eventually it increases the speed. Does it make sense?
Yes, sir.
Another thing that is actually that can be used is prefetching. So prefetching means quite simple. You fetch something from the memory before it is required into the cache. So how to do that? So you are going to need something. Let's say after 2 instructions, you just observe that that will be needed. You just bring that to cache. So that will improve the performance. But how to do that? So to do that, there are two ways to do. Either programmers can, on the depending on the requirement of variables or data that that program is going to need, can write a small code that will be actually fetching that data to cache, or compiler itself can do that. A programmer will write the program in the way it writes, and then compiler will insert the instructions, and this way, this prefetching can be done. But the thing that has to be ensured that while doing this prefetching, it should not be done in a way that by the time you are going to use the data, that is actually flushed out of cache. So this kind of care has to be taken, and that can be taken care of by compiler. So doing it via compiler will be a better idea to do, right?
Yes, sir.
And then there is one small thing. While performing certain operation, cache is actually locked up while it is performing some data transfer from memory to itself to have it more focused. So we call it lockup cache. So caches are made lockup free so that more than one miss requests can be entertained, and that may further be used for improving the performance of the system. So if this is okay, till this point we want to discuss cache and its performance. If there is any question, please ask, or otherwise we'll stop here and we'll discuss virtual memories and secondary memories in the next class. Any questions?
No, sir.
Syllabus for the end sem exam, at least memory will come, and if I'll do something else, that will also come. Any other questions?
No, sir.
Okay, then we'll stop here.